Okay, hi everyone. Today we're going to talk about the topic on pressure, right? And for pressure, we're going to look into two different things. Okay, let me swap this over. Right, so for pressure, we're going to look at two main concepts. The first one would be the pressure for solids. So the first part over here will be more for solids, right? And it's actually what we've learned before already, right? Second part over here is actually pressure in liquid. So this idea is a new idea, alright? And as mentioned in the lessons that this is actually a pure physics concept, okay? Usually in pure physics, but a lot of the application now spill in towards the combined physics. So it's also good for us to know some of these principles so that when we tackle these questions, we are very used to these questions. Okay, so without further ado, let's start off with the very first thing over here, which is here. Alright, so over here, let's recall that a force is either a push or a pull on that one object exerts on another object. Alright, so it is either push or pull on the person on a specific object, but pressure on the other hand is a bit different from force. Okay, and how is it different from force? Alright, so pressure over here is defined as the force acting per unit area. So you can think of it as force spreaded across an entire area. Okay, so let me jump back over here. So it is defined as the force, right, acting on a unit area. Okay, now, so usually for force, we normally annotate force as like a force on a single point or a force on a single object, right? And when we study forces, we only consider like just a summation of the forces and so on. But here we are concerned with the area. So we want to see like what is the feeling of the force on a small area versus a big area. So and then that's why we have the formula pressure is equals to force over area. Okay, and P equals to F over A in symbol. So this is the one that we need to take note over here, right? So for the units for pressure, right? P for pressure is in Newton per meter square. Why? Force is in newtons, area is in meter square. Combined together, you have Newton per meter square as the SI unit. Now, an alternative SI unit over here is known as Pascal. Okay, in honor of the person Blaise Pascal, who actually developed a lot of ideas on pressure. Okay, so short form we write PA for Pascal. Okay, so with this, let me show you who he is. Alright, so this is Pascal over here. Alright, is in the 17th century. Alright, and oh yes, one more thing is also pressure is a scalar quantity. Alright, so for example, it's not right for us to say like is the pressure upwards or downwards. We just say that the pressure applied on a single object and so on. Okay, alright, so now some examples of pressure over here is that we have like a force acting on a balloon, and you have like one piece of nail poking towards the balloon. So all the pressure or all the force is actually concentrated on that single nail. So because of that, right, the pressure is very high on the single nail. Okay, now in the same manner as you want to compare, given the same force, same kind of balloon, now you have many nails and the pressure spreads out over many nails, right? The force is spread out over many nails, so actually there's less pressure for each nail. Okay, and because of this, you may see people like lying on a bed of nails. It's perfectly fine to lie on a bed of nails. Okay, so and one more thing to take note is also for pressure, right? Over here you see a sponge, right? And how you orientate the brick will actually show you what is the pressure of the brick on the sponge. Okay, so for the brick, the left one, the area is a small area. Okay, so that's why you have a higher pressure and it pushes down more. if you were to put it horizontally, the brick has a wider area, and because of that there's lower pressure in, and it doesn't push down as much. Okay, so some application of pressure is the pointed tip of a thumbtack and the cutting edges of a scissors. Because they have small surface areas, the pressure is high. Okay, in a similar manner, the bulldozer, why does it have caterpillar tracks? Because of the wide base area, the caterpillar tracks actually have a low pressure, even though the bulldozer have a very high gravitational force. Because of that, the pressure is low, and the bulldozer can stay on the unstable ground or soil or sand perfectly fine. Right? One more application would be snowshoes. Why do we wear snowshoes in deep snow? Also because of pressure. Right? We want to spread out the pressure, spread out the force over a large area so that we have low pressure and we don't sink in so much. Right? So let's get back to our notes. Okay, let us fill in some blanks over here. Alright, let's fill in some blanks over here. So now, in order to analyze pressure, right, so the factors affecting pressure, right, mainly two factors. Right, so the first factor is we talk about the amount of force acting on the object. The second would be the area that you want to spread your force on. Okay, so analyzing this one over here, P is equals to F over A. Pressure is force over area. Now, if your force increase, because force and pressure is directly proportional, your pressure will also increase. Now, then if your area decreases, because it is inversely proportional to pressure, so your pressure will increase with a smaller area. The pressure is concentrated on a small piece of area. Okay, so when the force increase, your pressure increase. When the area decrease, your pressure increase. Okay, so this is how we analyze our pressure. Now, without further ado, let us take a look at the work example over here. Okay, we have a rectangular block of butter of dimension 10, 4, and 3 cm. Density, given density. And take note, we have to be sensitive to the units. So over here, this is in cm. The density over here is in meters cubed. Alright, so first we need to calculate the weight. Now, but the weight, okay, so let's have a framework on how to work on this kind of extended problems. Okay, so first we want to find out the weight. So weight is equals to mg. So this is the formula that we know for weight. Do we have g? Yes, g is 10 on earth. Now, the problem is actually m. Where can we find the mass from? Okay, is there any other mass given? We don't have any information of the mass given. So what do we need to do instead is we need to get the mass somewhere else, right? So where do we get the mass from? We need to get the mass from density, right? So density over here is equals to mass over volume. Now, density is given over here, right? So density is given, right? So from here, we can find the mass, right? But then the problem is, do we have the volume now, right? Do we have the volume of the butter? Actually can. We can actually find the volume of the butter from this information over here. So how do we write down our final response, or how do we write down over here is, first we need to look for the volume of the butter. Now the volume of the butter over here would be, let's standardize this. Let's change the cm to meters first to standardize with this unit over here, right? So we have 0.1 meters times 0.04 meters times 0.03 meters. So the volume is going to be equals to okay, we have 0.00012 meter cube. Okay, with this, the volume is done. We can look for the density. Density is equals to mass over volume. So density is 870 kg per meter cube. The mass is, I don't know the mass. The volume is this. Okay, so let's multiply this over to the other side, right? So in the end of the day, my mass is going to be 0.0 0.1044. Now this is in kilogram because this is kg per meter cube, and we multiply with the meter cube. Okay, alright, so with this, the last part over here is to find the weight. So weight is equals to mg. Now m is 0.1044 for the mass. Our g is going to be 10. Okay, make sure that it is kg and kg over here. So last but not least, we have 1.044 newtons, and this is equals to 1.04 newtons to 3 SF. Okay, over here. Now, B, let's find the maximum possible pressure when placed on the horizontal surface. So, pressure is equals to force over area. Now, in order to have a maximum pressure, okay, the force is going to be the same. The force comes from the weight of the butter. Okay, no matter how you orientate the butter, the weight will be the same. Now, so for the area, for maximum pressure, what about the area? We need a small area, right? So we definitely need a minimum surface area. So force is going to be 1.044 newtons, right? The area, okay, so what will be my area? The area will be made up of two smaller forces. Okay, I'm going to use meters over here. So I'm going to be 0.04 meters times 0.03 meters, the two smallest ones over here, and I have meters squared. So 1.044 divided by 0.04 divided by 0.03. So this is equal to 870 newtons per meter square, or Pascal also can. Okay, now for part C, find the minimum possible pressure. So P is equals to F over A. Now, in order to have a minimum pressure for a low pressure, force is the same. The area must be a large area. So we will need the maximum area. So force was 1.044 newtons earlier, right? For the area, I'm going to take the two biggest area. I'm going to take the 10 cm or 0.1 meters, okay, multiplied by 0.04 meters, right? So over here, let's do this, and we will see, okay, 261 minimum pressure, right? It can be Newton per meter square, or it can be Pascal. Okay, so you see these two questions over here, right? 870, 261. Really, one is big, one is small. Okay, so this is how we compare pressures. So this video is just to talk about the pressure in solid. Alright, the next video we're going to explore pressures in liquid. So stay tuned.